This will be a short presentation on telescope arrays and interferometry. This is a picture of the Very Large Array in New Mexico, and when it's in this particular position, as with all the antennas this close together, it doesn't have nearly the resolving power that it can at certain times. I'll show you a scale map here in a little bit that'll give you a better idea. But this is its photogenic position. It's easier to take a picture of it from the air when it happens to be in this configuration. So why have telescope arrays? Mainly it has to do with resolving power. The theta min equaling lambda divided by the diameter, or 1.22 times lambda divided by the diameter. The bigger you can make the diameter, the better resolving power you'll have. Combining the light from 2 or more telescopes gives you more light gathering power equal to the sum of their areas, and more importantly, it gives you an effective diameter for resolving power equal to the separation between the most widely separated parts of the array. So that's why you have arrays of telescopes. Here's a more realistic setting for the antennas there. It's somewhere in the neighborhood of half a mile between the antenna in this particular picture. There are 27 telescopes in the entire array. They actually have 28, but they bring one into a huge barn where they service it and perform upgrades on it and things like that. Here's a close-up of one of the antenna, and yes, those are stairs going up there. That's how you get up into the electronics of the thing and are able to work on it. When it's actually working, there usually aren't people on it. It's only if something goes wrong or if they want to upgrade something or service something that they'll have people on it. But most of the time, it's all run automatically. That's a picture of me when I was on a tour of this thing. I took a class at the headquarters for the Very Large Array, which is over about 60 miles away in Socorro, New Mexico. This was the brightest place I've ever been in my life. I've been on glaciers on Mount Rainier in sunny weather before, and this thing was way brighter than that. It's painted absolutely just bright white, and it ends up being more than half of your world when you're standing down there in the bowl of it. Here's a map that kind of has some parts to scale. The length of the arms here is somewhere in the order of, the red over here is the 3 arms of the array, but this is showing much more extent to it. It would actually extend off here to the left as well. But these are on the order of 12 miles here, and the distance from the tip of one arm to the tip of another is about 23 miles. And so when the antenna are in their full array, that's the effective distance from here to here. Here's a nice place to eat lunch nearby. After our tour, we went here and had a New Mexico specialty, which is a green chili cheeseburger, and they have pie too, so we all had that with lunch as well. Here's another array. This is called the Very Long Baseline Array, and it stretches from St. Croix in the Virgin Islands to Mauna Kea in Hawaii, and in between it's got antenna at Kitt Peak, Arizona, Pie Town, New Mexico. That's where the restaurant was that had the pie. Fort Davis, Texas, Los Alamos, New Mexico, Hancock, New Hampshire, North Liberty, Iowa, and Brewster, Washington. If you ever happen to drive up to Omak after you've gone past Brewster on Highway 97 there, across the river from the highway, you can see this particular radio telescope. There are a lot of things that look like this up there, but most of the antenna up there are for communication with geostationary satellites. But that's a very large array, this one. Very long baseline, thousands of miles. So this would give a radio telescope array a resolving power comparable to the best of the visible light telescopes, at least in the near infrared. Here's a picture of the radio antenna that's up at Brewster. For a long time, interferometry, which is combining signals from different telescopes to give you better resolution and light gathering power, for a long time it was only done with radio telescopes. Radio waves have much longer wavelengths and lower frequencies than visible light. The frequency might be measured in megahertz or even kilohertz, whereas for visible light the frequency is up 10 to the 14th hertz, something like that, very rapid changes, and it's much more challenging to do interferometry with visible light. However, it is starting to be done that way. This is a picture of this is an actual picture, it's kind of a dry place, the European Southern Observatory. Very large telescope is what they call it. Not a very clever name, but it's a group of 4 8-meter telescopes in the Atacama Desert in Chile, and you can see them here on this flat part that they put on top of a mountain. This is a nicer picture of the VLT, very large telescope. And in addition to those 4 telescopes, they have several other telescopes as well. This is a visible light interferometer telescope. There's another one on Mauna Kea in Hawaii called the Keck telescopes, which has just 2 telescopes in theirs, and they have a fairly long baseline there. Starting to be done in visible light as well. So interferometry, combining signals from 2 or more telescopes.